So this is the second review video for the final, and we're talking about Ampere's law. So just want to make sure everybody's clear. That's where we left off. We're going to keep going there, and sorry the last video was so long. I'll try and keep this one shorter. And so we've got Ampere's law, and we figured out what we needed to do to have a long straight wire, what Ampere's law is all about. We figured out a loop, wire in a loop. Now we're going to talk about wire for a solenoid. And so we've got this solenoid, and I kind of loosely drew it here. I think it's a little better than the one I've got in my notes, but maybe not quite. We've got some length L. We've got the current going in on one side and coming out on the other. So let's say that at the top the current is going into the page. At the bottom the current is coming out of the page. Well, every single one of these loops has that happening because it's a coil, right? It's a solenoid coil. So if you were to take your thumb and you put it into the page at the top, you'll notice that the B field goes like this. And the same thing for the bottom. The B field goes like this, in this direction. So that's what's going to happen inside our in fact, what really happens is this is the best way to create a uniform B field on the inside or for a region of space. We've now created a uniform B field. And what is the magnitude of that B field? Well, this is where Ampere's law comes in, and it's N mu naught L. Now if you notice, this doesn't say N and this doesn't say N, and that's because N is equal to the number of loops per length. Okay, so we have to take the total number of loops and divide it by the length of the object. So we could say, if you don't want to deal with this little thing, you could just say this. And why am I drawing an L on the end? This isn't an L. It has to be the current. So that's the current that's going through our solenoid. So those are the equations, Ampere's law. And most importantly about this situation is that we are creating creates a uniform magnetic field on the inside, okay? On the inside. So, of course, on the outside, you'd have your standard magnetic field, and it's going to drop off as you get further and further away. Nobody's going to ask you about that, so put your mind to rest about that one. So now, what if we have two long straight wires? So we've got two long straight wires. Now, we did this, it was tested, so chances of it being another question on another test are pretty slim, but we've got one long straight wire here, we've got another long straight wire here, and they're identical, they're perfect, unlike my drawing, and they're both have current, let's say they have current going in this direction. So here's I1 and here's I2. That's their current. There's a distance R between them. And so you can go through and you can figure out, oh, well, what is the B field for this thing? So you put your thumb along I, you curl your fingers, this goes into the page, this goes out of the page, this one goes out of the page, this one goes into the page, on each side of the wire. And then, of course, we're not talking about the top and the bottom. We're just talking about the circular in that plane. That's great. And if you do I cross B, so you go I, and then you cross it with B, which way is that force going? So put it along I, cross B, cross to B. How come I can't do the right-hand rule this morning? I cross B, F. Why isn't that working? The charges are moving in that direction. They're going to cross. Oh, it's not working. It's not working because you have to do the force from one to the other. So it's I, okay, so your force is 1 onto 2. So what does that mean, right? It's the force that 1 is doing onto 2. So you have, I'm not going to worry about all the other components. I'm just going to say I cross B, and then worry about the rest of the constants later. So I'll go like this. I'll say all times some K, right? Who knows? Don't get confused by this K. All I really want to do is the right-hand rule and figure out where we're going. However, because this is I2, 1 on 2, I have to do the current of 2, but the B field of 1, okay? So now I do the current of 2, the B field of 1, and I'm going to get that the force is in this direction, okay? So that's the force of 1, 2 for this situation. Now I don't want to do it, I don't want to draw my force right there. So let's, instead we'll put our force of 1 onto 2 right there. And we can do the same thing, force of 2 on 1, so that's going to be I1 cross B2 times some bunch of constants, who knows what, to get our right-hand rule going the other direction. Well, it's equal and opposite, right? So it should be that, and if we do it, where's I1? We're going to put our fingers along I1. I'm going to curl it to B2. B2 is out of the page toward us, so I1 curl B2 points my thumb in the F21 direction. So this is B2, this is B1. All right, so there you have it. That's how you do it. Okay, great. Now, what if one of those guys was flipped around? Okay, so let's come on over here and say we've got one of the currents, I1, for example, going this direction, I2 going in that direction, same R between them. But now let's do their B fields. So we use Ampere's law, we figure out the B field, and we go, oh, this one's going to go into the page on that side, it's going to come out of the page on this side, and over here it comes out of the page on this side and goes into the page. Is that right? Yes. Okay. So what are the forces? Force 1, 2. That's going to equal I2 cross B1 times some constant. We'll figure out what the real force is in a minute. I'm just trying to get the direction of these forces because you're going to have to get the direction of these forces. So it's important that you know what we're dealing with here. So fine, and I might rewrite this page. Well, I want you guys to see this video. I might rewrite this page for future courses, but I want you guys to see this video. So fine. So what do? We've got F1, 2. So this is the force of 1 onto 2. All right. So what's that force F1, 2? Is it going to be this direction or is it going to be this direction? I don't know. Let's find out. So we do F1, 2. I put my fingers along I2. I'm going to cross them to B1. All right. So that's toward us. And lo and behold, we get that the force is pointing to the right. What about for I1? I1, that's going to be the force of 2 onto 1. Should be minus and equal, so it should be this. So good, Newton's third law. And hopefully it will be. Let's do it. I'm going to put my fingers along I. I'm going to curl them to the B field from I2. And when I do that, I end up with a force that is definitely going in this direction. So there's the force of 2 on 1. And they're equal and opposite, and they point away from each other. Okay, and I don't know how well we did that in the class, but I certainly had a question about it on the test. So I don't know. I do like having those questions. I do like those questions. All right, and this is how you do it. All right, so let's get into what that force actually is. All right, so what is that force? Well, it's the Lorentz force law that we're using. And we've got current times some length. So we use the Lorentz force. So we go mu naught over 2 pi r. Okay, because why? We're using this situation right here. We're using, whoa. We're using this situation right there. Okay, it's a long straight wire. That's our B field, right, from one of the items. Okay, so if we're doing the force on 2, this is the B field of 1. Okay, so good. Now we're doing that. And so let's go back down here. So here's our B field. mu naught 0 times, let's do 1 onto 2. So it's I1 It's not I1, it's I2. Boom, 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 boom. Sorry, I can't keep both these equations. I need both equations to be seen at the same time. Okay. So I'm doing the B field from 1, and that is generated by I1. Okay, that's the B field for 1. Now I'm also multiplying that by the current that's going through 2, right? So I'm going to multiply that by I2, and I've got my mu naught I 2 pi r times those things. And now this is a force per length. Okay, so we could say it's the force per length, and that would be our force per length. So if we want just the straight up force, then we have to say, okay, 2 pi r I1 I2 times the length that we are doing this over. Okay, so the length would be some length like this that we could decide, I don't know, maybe we want that length to be 1 meter or something. So that's the force that you would have. This is called the force per length. This one here is the force per length. And that's typically what you get in this situation, right? Because your wires are super long, and you just want the force per length, right? You don't want the whole entire force for those wires at all points. So, but this would be the force over a certain section of length. All right? Force over section of length. And of course, we've got to do, I've got to, do the thing where if you figure it out for one, you do the minus and you figure it out for the other. All right? So, good. Nice. Love it. This also is the operational definition of a unit of 1 amp. So if our force per length is equal to 4 pi times 10 to the minus 7, and then we're putting 1 amp in each of the wires. We've got 1 amp. So we've got 1 amp squared. Well, 1 squared is 1. And then we're dividing by 2 pi, and if we keep them exactly 1 meter apart, then we end up with the fact that we've got 2 times 10 to the minus 7 is our force per length. This is the operational definition of 1 amp. So when you line 2 wires up together, 1 meter apart exactly, and you put 1 amp through them, the force that you'll have per length, Newton per meter, is exactly 2 times 10 to the minus 7 newtons per meter. And what you do is, if you're not reading 2 times 10 to the minus 7 newtons per meter, then you if you're below it, then you increase your current. If you're above it, then you increase your, you lower your current till you get it right. Then you know you've got 1 amp. So that's what I mean by that on the bottom of page 51 and the top of page 52. Okay, so let's get on with the Hall effect. We'll draw a little line here. Let's move towards the Hall effect. So we've talked about how we can have current induce a B field, and it does. Currents will definitely induce our B fields, but it goes vice versa, right? B fields will induce a current as well. So that's exactly what we're going to be talking about. So let's say we've got some strip of conducting material. It's a strip. It's not a wire. It's a flat strip. And it has some length L wide. Okay, I don't know why they didn't use width, but that's what we've got. So our current is going to be going this direction. That means our electrons are going in the other direction. Fine. So if our current's going this way, what is our B field? Do I care about the B field? And why are my B fields the same on both sides? I don't know. I don't think they should be. I think they should be into the page on the top side and toward us out of the page on the bottom side. So so I don't know. I don't know what is going on there. I should probably fix that. That's better. So fix that in your brain or on your piece of paper or whatever, but that's not correct. So, all right, so we've got our B field, and now we're going to notice that because of this, there's a potential that gets built up called the Hall potential. The Hall EMF, okay? And what is that? A voltage. A voltage is a potential, okay? It wants to, like gravity wants to push balls down hills. This or rocks or whatever, everything goes down the side of the hill. This is doing the same thing, okay? It's a potential that wants to push our charges in a certain direction. Okay, so what is that direction? I ruined my picture. Oh, this is an external B field. It's external. Dumb. It's the current flowing through an external B field. Okay, of course. That's why they're all going in the same direction. Okay, it's too early in the morning for me. Obviously, I need my Wheaties. Okay. Yes, it's an external B field that's pointing into the page. Okay, pointing out of the page. It's pointing straight at us. Look out! It's coming straight for us. So, right. So this is the external B field, not the one created by the current flowing. It's an external one. We've got current flowing down this strip no matter what, okay? And we've put it inside an external B field, all right? So the current has a drift velocity. It goes in a certain direction, and we've got this Hall effect happening, and the force then is going to be pressing us. Our Hall, let's do green. We'll do our Hall effect pointing up. Okay, so that's the force on our little guys that are our charges that are going through. So our Hall effect is driving charges, the holes, the positive charges, because that's the current, in the upper direction. So if we draw a picture, we have the same thing. Here's our wire, but this time I've got positive charges. All right, and they're all going on this side, they're all going in. Those positive charges are going to have a force that forces them in the end to be on this side. So all the positive charges end up over here going in this direction along the current. And the same thing goes for the negative charges, so the real electrons, but they end up over on this side going in this direction. All right, all our E are going in that direction. All of our holes are going in that direction. And they choose a lane. It's like driving in Britain or driving in the United States. They pick a lane, and either we or the British are backwards. I think it's the British. The British, we drive down the right side of the lane, and the Brits drive down the left side of the lane. Oh my gosh, they're left-handed. It's a left-hand rule in Britain. Gross. Japan, same thing. Oh, never thought about it that way. Why would you do the left-hand rule? That's gross. So we've got our Hall potential. We know which way our force is going. We can still use the Lorentz force law, but we wouldn't use the Lorentz force law. We would use the force on the charge. Okay, so we would use Lorentz forces of electric fields on charges. All right. What's my next trick? The magnetic force on a conductor with a current flowing through it. FILB. We did that already. So we did that. I'm going to move on. We're going to start talking about loops and the force of the current going through a straight up magnetic loop. All right, so let's do this. Let's do this thing. So we've got a wire. We've got a B field. I'm going to draw the B field. First, okay? And now we're going to draw our wire that is a loop. So our loop is going to come up. It's going to go like this. It's going to go down. It's going to go over there. And then. All right. And if we notice our current, we're going to send current in on this side. We're going to have current come back out on that side. So our B field is an external B field, not one that we are generating. We're working inside this B field. And we've got an axis of rotation. Goes right down the middle of our loop. We've got some width of the loop. And if you notice that the upper bar of our loop, the top part, I'll put a length over here too. We've got a length from there to there. We've got the top part, and the bottom part, these sections right here, when that current is going through those sections, it is not perpendicular to the B field. It's parallel with the B field. So it's not going to allow us to create a force. Now, if it does allow us to create a force, if it happens to be this thing's rotating about its axis and it is perpendicular to the field, the current that's going in the top section and the current that's going in the bottom section, those cancel out. Those, because one's going one direction, one's going the other, but the B field stays the same. So no matter what happens, it's either not giving you a current, not giving you a force, or when it does give you a force, the top and the bottom balance and they're equal. So either way, we're not doing anything with the tops or the bottoms, but we do get a force when we go along this side and when we go along this side with our current. So we do the same old thing. We say our force is equal to the length of the object times our current through the object times our B field external that we've got. But now, because it's rotating, we've got the sine of theta. So a better picture is the one I've drawn in the book. I wanted to draw this picture first, and this is my hand leaving trails. I wanted to draw a picture in the book first. So let's do this, and now we'll rotate this thing. Okay, so we're rotating like that. Okay, and so we've got some width, and we still have a length. We still have our current coming in this side, right? But now the whole thing has rotated about this axis. And I don't know which way we're rotating. Maybe we're rotating like that with some omega. All right, so the width, this is our radius of rotation. The width is 2 times the radius, right? And now we're going to see that the angle here is theta. And we can then say, oh, well, good, that angle theta gives me a maximum and a minimum. In fact, it oscillates back and forth between the two maximums and minimums as that thing spins around. And our torque is equal to R times the F that we have generated. So we've generated some force on this point, and that force is like this. So our torque is RF sine theta. All right, it's only RF when it's maxed out, right? Because the sine theta is 1 at that point. So in the end, we end up for one loop, because this is the area of one loop, and the area is equal to our width times our length. Then in the end, we end up with our torque is equal to, I got to put a sine theta here. All right, our torque is equal to our width times the length times our current going through the loop times the B field external that it's sitting in, external B field, times the sine of theta. And that is our, this is going to lead us to how we can get motors and generators, right? We've got things in a B field that are spinning around that's going to either be a motor or it's going to be a generator. So now what if we have a whole bunch of loops? We're going to have n of these loops. So now we have n loops. And we get the same equation. We just have to multiply by n. So our torque is equal to n times our width times our length times I times B external times the sine of theta. Okay, fine. And then to eliminate the, and of course that's A. This bit is A. To eliminate that sine theta, or not eliminate it, when theta is 90 degrees or, we're dealing with the sine of 1, right? So you could say that the maximum torque is equal to the number that we have times the area times the current times the external B field. NABE. Okay. Now we can get into some magnetic flux. How are we doing on time? We've got 15 minutes. I think we can get somewhere with this. I'm gonna have to record another one because we've got a ways to go yet. So do I want to continue here? Yeah, I'm gonna go a little bit. Okay, so magnetic flux. All right. First of all, why do we do a magnetic flux? Right? Because we want to know the EMF generated. Okay, so we're doing magnetic flux because we're looking for EMF generated. And we're doing that because essentially what we just did was we made a generator. Okay, so we've made a generator here, and we're going to take this generator and generate current with it. So we have to talk about magnetic flux. So we're generating an EMF, means we've turned our loop in a B field into a generator. Okay, so we're looking to find the EMF generated. Now, okay, so magnetic flux. We have some area. We just figured out what our area of our loop is, but we've got another loop. Now this time, our loop doesn't have, and we can do it. We could do this, and we could say, okay, here's our loop going down, and at some point we're going to put an ammeter in our loop. All right, so we can measure the current going through it. Okay, and then we're going to rotate it about that axis, right? Sure, eventually we're going to do that. But for now, we're not going to do any of that. And we're just going to have a loop of wire without any connections to anything else. So here's our loop of wire. It's got some area A, length times width. It has a normal to it. And now we're taking that loop of wire and we're putting it into a B field. I want to do this one specifically in this direction. So they are all parallel, even though they don't look like it. B field in that direction. What a terrible picture. Okay. I did this one with the normal next to it so that we can see that there's an angle between that and the normal that we're going to call theta. Okay, so there's the angle between the B field and theta. And of course, this is our external B field, all right? And let's just straight on get into flux. Flux is looked at with this phi. Okay, phi is the capital Phi is flux, and it's the B external times the A field, or times the A normal vector, or the total area, times the cosine of the angle between B and the normal. So we've got our area times the B external times the cosine of the angle. Now, that's just the amount of current passing through A. All right, so flux, that's it. Now, we'll have a change in flux. If it does change, it'll have different ways it can change. So it could change because the B is changing, okay? And then we'll multiply that by the cosine of A times theta. So B could be getting bigger or smaller. There's a change in B. It could be a change in the area. So maybe the area is getting bigger and smaller. So we have delta A. Or, oh, that's the second one. And it could be the third one where the B field and the area are staying constant, but theta here equals theta initial equals theta final. But over here, theta equals omega t. So then we would be doing cosine of omega t. And the whole thing is rotating, right? It would be rotating at some angular velocity omega. So those are our three options for having, you could combine these, right? You could have the area getting bigger, the B field getting smaller, and omega t changing. you could be doing that too, all right? We're not going to do any of that. We're going to choose one of these to work our problem because we don't want to make things too complicated. So that would be our change in magnetic field. Now it takes time for that change in magnetic field to happen. So when that change in magnetic field happens over a certain amount of time, then we get, if we put a negative sign on that, we're going to notice our EMF. Okay, and we could have N loops. So our EMF technically is equal to minus the number of loops that we've got times our delta phi over delta t. And that is how we're going to generate a current through. Now, why is there the negative sign here? Where does the negative sign come from? You guys know it. It's Lenz's law, and we can go through and figure out that it wants to increase the B field that's going through the area or decrease the B field that's going through the area because it's fighting the change in flux, okay? Much like Hooke's law, actually, that is fighting the change. It wants to put everything back to equilibrium. Well, this is doing the same thing, but with magnetic fields. Okay? So, that minus sign is Lenz's law coming through. Coming through in the end. Lenz's law. Okay. So I talked about how it can come about. We can change the 3 different things. Read section on using Lenz's law if you need to understand EMF and thereby the current direction that it's going to flow around the object, around the loop. So we've got those 3 ways. We've got these 3 ways of generating the EMF. These two ways are called motional. Why? Because the area is changing or the thing is rotating, the loop is rotating. So either the area is moving or the rotation is happening. That means motion. Okay, so these are motional EMFs. The change in magnetic field, getting larger, getting smaller, or whatever, that is not motional. That's the magnetic field simply getting bigger and smaller, and everything stays still. The area stays still, the cosine of theta stays still. So this one here is not motional. Okay, these are. So just to run that over and make sure that you guys are good with that. Now, what does that mean? That means that we get eddy currents. Okay, we get eddy currents developing from motional EMF. All right, so not emotional EMF, just motional EMF. I don't know why I can't avoid that joke. I just can't. I try to stay away from it. It's like candy. So, motional EMF drives eddy currents. And we went through this. We did an example of this, but I've got a pretty good picture drawn in the notes. And you'll notice that little eddy currents, if that was a sheet, okay, so imagine this is a sheet of some conducting material, all right? So it's a whole sheet. We've got this sheet, it's a solid sheet, not a loop, solid sheet, and it's moving in this direction. And it has a B field that it's moving through. So we can draw a B field here that it's moving through. And what is going to happen, we're going to develop motion, eddy currents as it's going through that B field, but only if there's a change in flux. Okay, so that means in our situation, it looks like it's going through the B field proper. So in this situation, we have to have a change in flux. But if we're moving into or out of, so let's say this is the edge of the B field, right here, and now we're going to be moving out of that B field. As we leave that B field, that gives us our motional EMF. So our V is going in that direction. Our area is going to be getting smaller, and that's going to drive eddy currents in our plate, our little plate that's going, leaving the B field region. Okay, we've got our eddy currents. How much time we got? All right, I'm going to call it here we'll talk more about eddy currents in a bit. I gotta have a cup of coffee or something before we start doing FILB right hand rule stuff and looking at which direction the eddy currents are gonna go. We'll do that when we come back. The same bat time, same bat channel. All right.